Okay, it's a good problem. I haven't seen one like this before, so props to your professor for coming up with a fresh one. So I drew a picture here of the cylindrical water tower and imagining this spiral staircase going up and around and finishing at the point that's directly at top of where it was. And I thought, okay, how are we going to get a feel for how long it takes to get around here if it goes around exactly once but also goes up this high? So I thought, okay, why don't we think about chopping this thing, like cutting that cylinder and then rolling it flat. And then that spiral staircase that you see going up like that would really just be going up in a straight line. And the distance around this thing, that circumference, when you lay it flat, would be still the same length, of course. You just kind of unroll that thing and it's going to lay flat. And that distance is the circumference, which is 2 pi r. Of course, the height of this thing is the same as the height of the cylinder. And now you can think of that length of that staircase moving efficiently right up one time around, and now you see, okay, we've got an a squared plus b squared equals c squared situation here. So we could think of L as being the hypotenuse and C being the circumference and H being the height. So you go C squared plus H squared equals L squared. So if you think about that equation, you say, okay, C squared plus H squared equals L squared. And so L is the square root of C squared plus H squared. And we know, so that's kind of what I have right down here. And instead of putting C in, of course, the circumference, I replaced the C with the circumference with what the circumference formula, which is 2 pi r. So 2 pi r quantity squared plus H squared square rooted is going to be what L is. Now, the problem asks you, it kind of refers to one where you guys were asked earlier in the year to come up with L as a function of H. So that means we can't have this R in here. So what we have to do is substitute R for something equivalent to it. So I went ahead and squared 2 pi r and got 4 pi squared r squared if you just square each one of those things. So what we need to do is get rid of this r squared and replace it with something that's equivalent to it. So you go over to the part of the problem that says the volume of this thing has to be 935,763 whatever it is, cubic feet or something like that. And the volume of a cylinder is pi r squared h. So what I can do is get r squared by itself by dividing by h and dividing by pi. So you get r squared equals this junk over pi h. And so I thought, rather than dividing by h, why don't we think of that as multiplying by h to the negative first power? And just take this thing, which is r squared, and drop it right in there for that r squared. Take r squared out and replace it with something that's equal to it. And so instead of having 4 pi squared r squared, you have 4 pi squared times this mess, which is this stuff. So that there is c squared plus h squared square rooted raised to the 1/2. So this is a really ugly, thing. This is going to be a calculator problem for sure. So I simplified a little bit and said, hey, I've got pi squared up here and a pi down there. So you cancel one factor of pi out and you wind up with a pi. I did 4 times 935,763 and got 3 million, so this number here. So this is really a formula for L in terms of H that's all cleaned up for a cylinder that's going to have that volume to it. So that's a decent chunk of algebra there. But the question is really asking, we want to minimize this length. So if you have a formula for that length and you want to minimize it, you take the derivative and set it equal to 0. So this derivative is going to be, kind of a mess. So I'm going to say L prime is bring the 1/2 down in front. What's inside here is not going to change at all. So it's going to be that 3743052 pi times h to the negative 1 plus h squared to the negative 1/2 multiplied by the derivative of what's inside. Remember, we've got the chain rule going on here. So the derivative of what's inside is the derivative of this thing, where I take that negative 1 down in front and multiply it by that. So negative 3743052 pi. H, drop the power by 1, so h to the negative 2. And then take the derivative of h squared, which is just going to be 2h. And there we go. So we did the chain rule. We took the derivative of the outside function and we multiplied it by the derivative of the inside function. And we're curious, when is this mess going to be equal to 0? So we set it equal to 0. So if you clean this up algebraically, you're going to have this thing, you're going to have a fraction bar, first of all. We've got the 1 on the top, and we've got the 2 on the bottom. That's just simply this 1 and this 2. This stuff is raised to the negative 1/2, so it's going to go down here in the denominator. So I'm going to take that 3743052 pi h to the negative 1 plus h squared. That's all to the negative 1/2, so it comes downstairs and goes to the positive 1/2. And then we've got this stuff here, which is left in the numerator. So negative 3743052 pi h to the negative 2 plus 2h. And here's the beauty of these problems that come from these Pythagorean relationships. You always wind up having this square root thing. You take this friggin' derivative of this thing, which always winds up in a negative 1/2 power, which sends this junk down to the denominator, and none of that crap matters at all, because if you're setting a fraction equal to 0, which is what we're doing here, here's the numerator, here's the denominator, setting it equal to 0, the way that a fraction is equal to 0 is when the numerator is equal to 0. So all we have to do is find out what value of h solves that equation. So I'm going to come over here and write that equation, that negative 3743052 pi times h to the negative 2, which really means over h squared, plus 2h has to equal 0. Well, algebraically, why don't we bring this over to the other side? So we're going to get 2h equals positive 3743052 pi over h squared. And the way to solve this is cross multiply. Take this stuff and multiply it up here, and take that 2 and put it down there, and we're going to get h cubed equals 3743052 pi all over 2. And when we get that, whatever number that is, I guess I can go get that off my calculator here. And let's see. And I got 5879572.3, repeating, I think. And that's what h cubed is, so h is the cube root of that number, cube root of this, which turns out to be 180.488. So that's gold, because that tells us when this function here, when this L function is going to have its slope of 0. And, God knows what that thing looks like. Probably, if you were to graph that thing, it would probably kind of look like a Nike swoosh thing. These things, those square root functions look like that. And what you've just found is that place where the length is going to be a minimum. So I think the question actually asked, I don't have it in front of me now, but the question actually asked, what are the dimensions of the water tower going to be? Well, now that you have the height being about, we can say ballpark, that's 180.5 feet, you can go find the formula where you have r squared, which is right up here, and you can just plug that value of 180.5 in there and find out what r squared would be, and then take its square root. So let's hold on for a second here. So I just kind of communicated all that information that we had on the last page there, that the height turns out to be 180.5. R squared, the formula for that was 935,763 divided by pi times h, so I just threw h in there, got a number for that, and since that's r squared, the radius would be the square root of that, which is about 40.624. So I think the question asked for the dimensions of the thing, so the height would be, that 180.5, and the radius would be 40.624, yada, yada, yada. So hopefully that helps. As like I said, it's a good problem. Hopefully this helps you out.